These are the answers to the electron configuration practice quiz. The diagram at right represents 3 different electronic transitions labeled as A, B, and C. Each transition is associated with a particular form of electromagnetic radiation, or EMR. For the calculations, you may use the following equations and constants. So we have the equation involving the speed of light and wavelength and frequency. And we have the equation involving energy, Planck's constant, and frequency. Now we can tell that based on the different lengths of the arrows, that the electromagnetic radiation released in transition A should have the highest energy, the highest frequency, and the shortest wavelength. We can also tell that the EMR released in transition C should have the lowest energy, lowest frequency, and longest wavelength. All right, let's go ahead and do the calculations. Number 1, A. Calculate the frequency of this form of EMR, which has a wavelength of 103 nanometers. We'll use the speed of light equation, and since we are solving for the frequency, frequency equals speed of light divided by wavelength. But the speed of light is in meters per second, and we have a wavelength in units of nanometers. So we have to convert this from nanometers to meters. So how do we do this? We use a conversion factor that has 1 meter on the top and 10 to the 9 nanometers on the bottom. And we get 1.03 times 10 to the negative 7 meters. Then we get a final answer in units of 1 over seconds, or hertz, 2.91 times 10 to the 15th. In part B, calculate the energy of this form of EMR. Since we already have the frequency, we can just multiply Planck's constant times the frequency, and the seconds will cancel out. Our answer will be in units of joules. So if we do this math, we get 1.93 times 10 to the negative 18 joules. Okay, on to part 2. This time we are given a frequency, and we're going to calculate the wavelength. So we have the same speed of light equation, but we're going to be solving for the wavelength. Wavelength equals speed of light divided by frequency, and I've written the frequency in units of 1 over seconds, so you can see how the units will cancel out the seconds part, and we get an answer on our calculator, 6.56 times 10 to the negative 7. But the units right now are in meters. It says express your answer in units of nanometers. So we have to convert this value from meters to nanometers. We're going to multiply by 10 to the 9, because there are 10 to the 9 nanometers in 1 meter. And if we do this math, we get 656 nanometers. Now, on to part B. Calculate the energy of this form of EMR. Let's just use the Planck's constant equation. Multiply Planck's constant times the frequency that was given in the problem, and the seconds will cancel out. We get our answer in units of joules. 3.03 times 10 to the negative 19 joules. And now on to number 3. We are given the energy in joules, so we're going to first calculate the frequency by using the Planck's constant equation. This time, since we already know the energy, we're going to solve for the frequency by doing energy divided by Planck's constant. So we'll have joules cancel out, and our answer will be in 1 over seconds, which is hertz. Our calculator will give us an answer of 1.60 times 10 to the 12 hertz. We can then take that frequency, and using the speed of light equation, we can calculate the wavelength. So wavelength equals speed of light divided by the frequency, and we're going to get an answer in meters. We get 1.88 times 10 to the negative 4, but that's in meters. Let's again multiply by 10 to the 9 to convert from meters to nanometers, and our answer is the wavelength in meters, 1.88 times 10 to the 5th nanometers. All right, let's review the diagram that we saw earlier. Transition A should have the highest energy, highest frequency, and shortest wavelength. Transition C should have the lowest energy, lowest frequency, and longest wavelength. So therefore, in number 4, which transition has the longest wavelength? That would be C. Which transition has the highest frequency? That's A. And highest energy? That's A as well. Of the 3 forms of light given in number 5, ultraviolet light has the highest energy, and infrared light, of the 3, has the lowest energy. So therefore, transition A, which has the highest energy, would be giving off ultraviolet light. Transition C, which has the lowest energy, would be giving off infrared light. And in the middle, transition B is giving off visible light. All right, on to number 6. We saw graphs like this on the exit card. 2 of the following graphs are correct. We know that energy and frequency are directly proportional, and we know that wavelength and frequency are inversely proportional. Okay, number 7. Let's take a look at the Bohr model of the atom. We have a nucleus in the center, and we have the first energy level called the ground state, and there's an electron at that level. And then we have various higher energy levels known as excited states. So if the electron absorbs energy, it can move from a lower energy level up to a higher energy level, which is farther away from the nucleus. So choice A says that when an electron absorbs energy, it moves from an excited state to the ground state. That's backwards. Choice B, same problem. It says absorbs energy, but then says from a higher level to a lower level. That's backwards. And then choice D, when an atom releases energy, it should be moving from an excited state to the ground state. So D is also backwards. Correct answer is C. When an atom releases energy, it would move from a higher level to a lower level, just like we saw in the diagram at the very beginning of this practice quiz. All right, next question in number 8, we are given 3 rules, and our job is to look at each diagram separately and figure out which one of these rules is broken. So we're starting with the first diagram on the left. Notice that all of the arrows are not opposite. They're both up. We have just broken, in this diagram, the Pauli exclusion principle that states that the 2 electrons in the same orbital must have opposite spins. In the next diagram, if we focus on the 3p sublevel, we see that there is an up arrow and a down arrow in the same orbital. This breaks Hund's rule, which states that when 2 or more orbitals have the same energy along the p sublevel in this case, each orbital in that sublevel must have a single electron in it before an orbital can get a second electron. So we broke Hund's rule. And now on to the third diagram. The last part of the configuration has put an arrow, an electron, into the 3p sublevel, and it completely skipped the 3s sublevel, which is empty right now. According to the Aufbau principle, the electrons must fill the lowest available energy levels, so this is an example of breaking the Aufbau principle. All right, on to the next question, in which you need to write the incorrect electron diagram for a certain element. And you must break one of the rules when you draw the arrows in the diagram. So we're starting with, on the left, lithium. So lithium, the correct electron configuration for lithium, which contains 3 electrons, is 1s2, 2s1. If we're going to break the Aufbau principle, and there's lots of different ways to do this, we need to put an electron into a higher energy level than it would normally be. So for example, that would be one way to break the Aufbau principle. Another way to break the Aufbau principle might be like this, or possibly like this. Notice that we still have 3 electrons, but they're not in the lowest available energy levels. So lots of different examples, lots of ways to break the Aufbau principle. All right, now we have beryllium, which has 4 electrons. The normal electron configuration is 1s2, 2s2. If we're going to break the Pauli exclusion principle, instead of these arrows having opposite spins, they might look like this. And then finally, if we're going to break Hund's rule, here's what carbon should look like with its 6 electrons, 1s2, 2s2, 2p2. We have the last 2 arrows in separate boxes on the 2p sublevel. So breaking Hund's rule would look like that. All right, number 10. For each element, indicate how many unpaired electrons, which is a single arrow in a box, are present in the ground state electron configuration. So it might be nice to go ahead and show you these energy level diagrams and verify how many unpaired electrons there are. So lithium, which has 3 electrons, would look like this with 1 unpaired electron in the 2s sublevel. Boron has a total of 5 electrons, and when we finish the electron diagram, we have 1 unpaired electron in the 2p sublevel. Carbon would have 2 unpaired electrons. Nitrogen would have 3 unpaired electrons. Oxygen has only 2 unpaired electrons. And fluorine has only 1 unpaired electron. Now when we get to neon, every box is full, so there are 0 unpaired electrons. Sodium has 1. Magnesium would have 0 because the 3s sublevel is full. Aluminum would have 1 unpaired electron. Silicon would have 2 unpaired electrons. And phosphorus would have 3 unpaired electrons. It's easier, in my opinion, to draw the energy level diagram than just to try to think about it looking at the periodic table. All right, number 11. We are given an electron configuration which is 1s2, 2s2, 2p6, 3s2, and 3p1. That is a total of 13 electrons. So this is aluminum on the periodic table. Which of the following is an electron configuration of another element that is in the same group or family? So boron has 5 electrons, 1s2, 2s2, 2p1. Gallium has 31 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. So there is no choice that represents gallium, but the correct answer is A, because that is boron and that is in the same family as aluminum. All right, number 12. What is the ground state electron configuration for iron? Iron has 26 electrons, so it's going to have 1s2, 2s2, I'm just sort of following along the periodic table, 2p6, and then we keep going, we're trying to get to iron, 3s2, 3p6, 4s2, and now it's going to be 3d, 1, 2, 3, 4, 5, 6. So that is our electron configuration, and the correct answer is B. All right, moving on to number 13. What element is represented by the electron configuration shown above? You cannot just look at the last portion and assume that because it ends with 6s2 that it must be barium. I have written these subshells and sublevels in various orders, so let's make sure we take care of all of the sublevels. So here on the periodic table, we have everything up through argon, so 1s2, 2s2, 2p6, 3s2, and 3p6. I'm shading in the periodic table as I go. Then we have 3d10 and 4s2. That would get me as far as zinc. Then we have 4p6, which takes me to the end of period 4. That's krypton so far. That's 36 electrons. What comes after 4p6 on the periodic table is 5s2, so up to strontium. 4d10, I'm now at cadmium. 5p6, I'm up to xenon. 6s2, now I'm at barium, but there are still 21 more electrons that I have to take care of. So 4f14 and 5d7, I would stop at element number 77. The symbol is IR, and that is iridium. Now, was there another way to do this? Yes, all you have to do is count the total number of electrons in the superscripts, and you would get exactly 77 electrons, which is the atomic number of iridium. All right, number 14, we have silicon, germanium, and tin. They are all located in group 14, and they would have 4 valence electrons. This chart is from your most recent packet entitled Electron Configuration Patterns. So 4 valence electrons for carbon, silicon, germanium, and tin. Number 15, the nonmetals in group 15, they're going to have a -3 charge, so they all would gain 3 electrons in order to become a stable ion. That includes nitrogen, phosphorus, arsenic, and antimony. Number 16, we're not talking about fluorine, which has 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1s2, 2s2, 2p5. We're talking about the electron configuration of the fluoride ion. Now, since fluorine would normally gain 1 electron and have a -1 charge, to fill out the outer shell, we have to add 1 more arrow to the diagram. So the correct configuration is 1s2, 2s2, 2p6, which is the same as the noble gas neon. All right, number 17, we're going to write the complete electron configuration for each of the following elements: silicon, selenium, strontium, and antimony. All right, let's start with silicon. Silicon has 14 electrons, so 1s2, 2s2, and 2p6. That gets us as far as neon, so we keep going. 3s2, now we're up to magnesium, and then finally 3p2. So that is the answer for silicon. Moving on to selenium, we have 34 electrons. So if we stop at 3p6, that would be at argon. Let's keep going. 4s2 would stop at calcium. Let's do a little bit more. 3d10 would stop at zinc. And finally, to get to selenium, it's going to be 4p4. So that is the electron configuration for selenium. Now, strontium has a total of 38 electrons. So everything up through krypton, which would stop at 4p6, we have to put the last 2 electrons. For strontium, it's going to be ending with 5s2. And then finally, antimony, which has 51 electrons. I'm going to add a little bit more to the strontium electron configuration. So I add 4d10. If I stop right there, that would be cadmium, Cd. I have to add 3 more electrons, 5p3, and that is the electron configuration for antimony. Okay, in number 18 it says go back and circle the valence electrons in each of the electron configurations that you wrote. So for silicon, it has 4 valence electrons, so we'll circle the last 4 electrons in the configuration, 3s2, 3p2. Selenium has 6 valence electrons, and I have written the electron configuration slightly differently than before. I reversed the 4s2 and the 3d10 to make it easier to identify. But as long as you circle 4s2 and 4p4, that would be correct. Strontium, it's going to be just 2 valence electrons, so I circle 5s2. And antimony, there should be 5 valence electrons. So again, I switched the order of the 5s2 and the 4d10, but you don't have to do that. As long as you circle 5s2 and 5p3, that would be correct. All right, we now have a chart to fill out in number 19. So our first element is bromine. Bromine has 35 electrons, and the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 in either order, and then 4p5. It has a total of 7 valence electrons, which you can see from this chart. All of the halogens in group 17 have 7 valence electrons. It's going to form a -1 ion, so it's going to gain 1 electron. And when it goes from 35 to 36, it will have the same number of electrons as krypton, the noble gas. Our next element in this table is phosphorus, which has 15 electrons, 1s2, 2s2, 2p6, 3s2, and then 3p3. It has 5 valence electrons, just like nitrogen and arsenic and antimony, and it's going to form a -3 charge as a stable ion, so it's going to gain electrons. And 15 is how many phosphorus has. If it gains 3, it's going to have 18. That's the same as the noble gas argon. Our next entry in the table does not tell us what the element is, but that's 5 electrons total for the electron configuration, so that would be the atomic number of boron. Boron is in group 13, and it would have a +3 charge. It has 3 valence electrons. It's going to lose 3 electrons and have the same electron configuration as helium, because it only has 5 electrons. So if it loses 3, it would go back to 2. Our next entry in this table has a total of 37 electrons, and that works out to be rubidium. It has only 1 valence electron. It would lose 1 electron to have a +1 charge, and going from 37 to 36 would mean that it has the same number of electrons as krypton when it becomes an ion. Now we have a -2, which means gain, and a +2, which means lose. But what are these elements? Well, if neon has 10 electrons, what element would have gained 2 electrons to now have 10? It must have had 8 to start with. So oxygen has atomic number 8, 1s2, 2s2, 2p4. The total number of valence electrons, including the s's and the p's in the outer shell, would be 6. And for the other element, if it lost 2 electrons and now it has the same number as argon, which is 18, that means it must have had 20 to begin with, and that would be the atomic number of calcium. Calcium electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, and then finally 4s2. That is the outer shell, 4s2. So it has only 2 electrons in the outer shell. All right, the table is now complete. On to number 20. We have to write the configuration for the atom and then the ion. So starting with nitrogen, the atom has 7 total electrons. 1, 2, 3, 4, 5, 6, 7. So that is nitrogen, the atom. Since it will gain 3 electrons to form a stable ion, I'm going to write nitrogen, the ion, by adding 3 more electrons to fill out the outer shell. Aluminum starts with 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's what aluminum looks like. Now aluminum is not going to gain 5 electrons. All it has to do to form a stable ion is lose 3. Let's take away 3 electrons from aluminum. 1, 2, 3, and that would be the electron configuration of the aluminum ion with a +3 charge. All right, our next example, sulfur, which has 16 electrons total. 10, 11, 12, 13, 14, 15, 16. So that's what sulfur looks like as an atom. All sulfur needs to do to gain 2 electrons and fill out its outer shell, now it's going to have a -2 charge. So sulfur, the ion, looks like that. And then finally we have potassium. Potassium starts out with 19 electrons. So all potassium needs to do to form a stable ion is to lose 1 electron. So when that 4s electron is gone, then that is the arrangement of the 18 electrons for the potassium with a +1 charge. All right, well, that question is the end of the electron configuration practice quiz. I hope that these answers and explanations were helpful. Thanks for watching, and good luck studying.